Hello, this is Tim Smith, the Academic Support Coordinator of St. John's River State College, St. Augustine campus. This video, Complex Zeros of Polynomial Functions, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended that you watch the video Polynomial Functions prior to viewing this video. In this video, we'll be reviewing polynomial functions, discussing rational zeros, irrational zeros, complex numbers, complex zeros, and imaginary zeros. A polynomial function is one of the form f of x is equal to a sub n times x to the n, plus a sub n minus 1 times x to the n minus 1, plus a sub n minus 2 times x to the n minus 2, and so on to a sub 1 times x plus a sub 0, where n is a non-negative integer and a sub n is not equal to 0. The numbers a sub 0, a sub 1, a sub 2, and so on, including a sub n, are called coefficients of the polynomial. The number a sub 0 is the constant term, and the number a sub n, the coefficient of the highest power exponent, is the leading coefficient, and a sub n times x to the n is the leading term. As an example, f of x is equal to x cubed plus 4x squared plus x minus 6. Let's take the same function, f of x is equal to x cubed plus 4x squared plus x minus 6. This is a third-degree polynomial with a positive leading coefficient. The first zero is the y-intercept. Setting x equal to 0, we get the point 0, negative 6. To find the rational zeros associated with the x-intercept, we set f of x equal to 0. We then look at the constant term 6 over the leading coefficient 1 for possible zeros. The factors of 6 over 1, or 6, is 1, negative 1, 2, negative 2, 3, negative 3, 6, and negative 6. Let's first start with negative 1. F of negative 1 equals negative 1 cubed plus 4 times negative 1 squared minus 1 minus 6, which equals negative 4. Negative 1 is therefore not a zero of the function, but it may be useful as a test point later on. Next, let's try f of 1, which is 1 cubed plus 4 times 1 squared plus 1 minus 6, which equals 0. Therefore, 1 is a rational zero of the function. The point 1, 0 is a point on the graph, and x minus 1 is a factor of this polynomial. Next, we use polynomial division. X cubed plus 4x squared plus x minus 6 divided by x minus 1. X squared times x minus 1 equals x cubed minus x squared. Subtract to get 5x squared, then bring down the x term. The next term will be 5x. 5x times x minus 1 is 5x squared minus 5x. Subtract to get 6x, then bring down the negative 6. The last term will be positive 6 times x minus 1 equals 6x minus 6 with no remainders. Therefore, the original function may be factored into x minus 1 times the quantity of x squared plus 5x plus 6. X squared plus 5x plus 6 factors into x plus 2 times x plus 3. This gives us the two other zeros, negative 2 and negative 3, and the points negative 2, 0 and negative 3, 0. We can now plot the known points. Since this function has a leading term with an odd exponent and a positive coefficient, we expect the function to go to positive infinity with increasing positive x's and negative infinity with increasing negative x's. This, combined with the 5 points, allows us to sketch the graph with some degree of accuracy. For another example, let's evaluate the function f of x is equal to negative x cubed minus x squared plus 3x plus 3. Again, we can find the y-intercept by setting x equal to 0. F of 0 is 3. Next, we set the polynomial equal to 0 and look for possible factors. These will come from the constant term divided by the leading coefficient, or 3 over 1, or 3. Possible rational zeros will then be 1, negative 1, 3, and negative 3. We'll start with 1. F of 1 equals negative 1 cubed minus 1 squared plus 3 times 1 plus 3, which equals 4. 1 is therefore not a zero of the function, but 1, 4 may be useful as a test point later on. Next, we'll look at f of negative 1. Minus negative 1 cubed minus negative 1 squared plus 3 times negative 1 plus 3 equals 0. Therefore, negative 1 is a zero of the function. The point negative 1, 0 is a point on the graph, and x plus 1 is a factor of the polynomial. Next, we'll use polynomial division. Negative x cubed minus x squared plus 3x plus 3 divided by x plus 1. Negative x squared times x plus 1 equals negative x cubed minus x squared. Subtract to get 0. Next, bring down to 3x plus 3. 3 will be our last term, times x plus 1 is 3x plus 3, and this gives us no remainder. Therefore, the original function factors into x plus 1 times the quantity of negative x squared plus 3. Negative x squared plus 3 can factor into negative x plus the square root of 3 and x plus the square root of 3. This gives us the two other zeros, the square root of 3 and negative square root of 3. These will also be points on the graph, the square root of 3 is 0 and negative square root of 3 is 0. Since the square root of 3 is irrational, we call these 2 points irrational zeros. The square root of 3 equals approximately 1.73. So we can give a good estimate of the position on the x-axis, and these points can still be used as points on the graph. We then add the previously established points to our graph. Since the polynomial has a degree of 3 with a negative leading coefficient, the function will go to negative infinity with more positive x's and positive infinity with negative x's. This, along with the known points, gives us enough to approximate a graph of the function. Complex numbers are numbers of the form a plus bi, where a and b are real numbers, and I is the imaginary unit, and I squared is equal to negative 1. We can depict this graphically. Real numbers are complex numbers of the form a plus bi, where b is equal to 0. Imaginary numbers are complex numbers of the form a plus bi, where a is equal to 0. A variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the form f of x is equal to a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2, and so on until a sub 1 times x plus a sub 0, where a sub n minus 1, a sub n minus 2, and so on, including a sub 1 and a sub 0, are complex numbers, and a sub n is not equal to 0, n is a non-negative integer, and x is a complex variable. A complex number r is called a complex 0 of f if f of r is equal to 0. Every complex polynomial function of degree n greater than or equal to 1 can be factored into n linear factors of the form f of x is equal to a sub n times the quantity of x minus r sub 1 times the quantity of x minus r sub 2, and so on times x minus r sub n, where a sub n, r sub 1, r sub 2, and so on, including r sub n, are complex numbers. This means that every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. A polynomial function may have zeros that are not included in the real number system. For example, zeros of the form a plus bi, where b is not equal to 0. Suppose f is a polynomial whose coefficients are real numbers. If r equals a plus bi is a 0 of f, the complex conjugate r equals a minus bi is also a 0 of f. A polynomial function f of odd degree with real coefficients has at least one real 0. As an example, let's evaluate the polynomial function f of x is equal to x cubed minus 3x squared plus 2x minus 6. As a third-degree polynomial, we can expect three complex zeros, at least one of which must be a real zero. As before, we can arrive at the y-intercept by solving for f of 0, which equals -6. To find x-intercepts, we set the function equal to 0. Possible rational zeros can be found by evaluating the constant term 6 over the leading coefficient 1, which gives us possible rational zeros of 1, -1, 2, -2, 3, -3, 6, and -6. We'll start with f of 1. f of 1 equals 1 cubed minus 3 times 1 squared plus 2 times 1 minus 6, which equals -6. This is not a zero of the function, but 1, -6 can be saved as a test point. Next, we'll try f of 2. f of 2 equals 2 cubed minus 3 times 2 squared plus 2 times 2 minus 6, which equals -6. Again, this is not a zero, but 2, -6 can be saved as a test point. Now let's try f of 3. f of 3 equals 3 cubed minus 3 times 3 squared plus 2 times 3 minus 6. This equals 0, which means 3 is a zero of the function, and the point 3, 0 is a point on the graph, and x minus 3 is a factor of the polynomial. This also satisfies the theorem of a polynomial function with an odd exponent in the leading term, having at least one real zero. Next, we'll complete the polynomial division. X cubed minus 3x squared plus 2x minus 6 divided by x minus 3. X squared will be the first term. X squared times x minus 3 is equal to x cubed minus 3x squared. Subtract to get 0. Bring down 2x minus 6. 2 will be the next term. 2 times x minus 3 equals 2x minus 6. This gives us a 0 remainder. The polynomial function can now be factored into x minus 3 times the quantity of x squared plus 2. Next, set x squared plus 2 equal to 0. X squared equals -2. Then x equals plus or minus the square root of -2. The two additional zeros are then I times the square root of 2 and -I times the square root of 2. These zeros are both imaginary numbers and as such do not represent points that may be graphed. They are also complex conjugates of each other as described in the theorem. To assist in graphing, we can find another test point. f of -1 equals -1 cubed minus 3 times -1 squared plus 2 times -1 minus 6, which equals -12. Since the leading term is positive with an odd exponent, the end behavior will be increasing with increasing positive x's and decreasing with increasing negative x's. These points and the end behavior may be graphed, but with two imaginary zeros, it becomes difficult to graph this function accurately without techniques learned in higher math classes or by using a graphing calculator. As another example, let's find the complex zeros for the function x cubed minus 8x squared plus 25x minus 26. This is a third-degree polynomial, so there will be three complex zeros, at least one of which must be a real zero. We can first solve for f of 0 to get the y-intercept 0, -26. As before, we'll look for possible rational zeros by evaluating the factors of the constant term over the leading coefficient, which is 26 over 1 or 26. These factors are 1, -1, 2, -2, 13, -13, 26, and -26. Let's first try f of 1. 1 cubed minus 8 times 1 squared plus 25 times 1 minus 26 equals -6. Therefore, 1 is not a zero, but 1, -6 is a solution for the function. Next, let's try f of 2. This is 2 cubed minus 8 times 2 squared plus 25 times 2 minus 26. This simplifies to 8 minus 32 plus 50 minus 26, which equals 0. Therefore, 2 is a zero of the function, and x minus 2 is a factor of the polynomial. Using polynomial division, we take x cubed minus 8x squared plus 25x minus 26 and divide it by x minus 2. X squared will be our first term. times x minus 2 is x cubed minus 2x squared. Subtract to get negative 6x squared, then bring down the 25x. Minus 6x times x minus 2 equals negative 6x squared plus 12x. Subtract again to get 13x, then bring down the negative 26. 13 will be our last term, times x minus 2 is 13x minus 26 with no remainder. Therefore, the polynomial factors into x minus 2 times x squared minus 6x plus 13. X squared minus 6x plus 13 is not easily factorable, so let's use the quadratic formula to find the two remaining zeros. The formula starts with x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. In this case, a will be 1, b will be negative 6, and c is 13. Fill in the values and simplify. 4 times 1 times 13 equals 52. 36 minus 52 is negative 16. The square root of negative 16 is 4i. Factor 2 from each term to arrive at x equals 3 plus or minus 2i. Our final factorization of the polynomial is then x minus 2 times x minus 3 plus 2i times x minus 3 minus 2i. The two additional zeros are then 3 plus 2i and 3 minus 2i. Note, these are a conjugal pair as predicted previously. The question only asks for the three complex zeros of the function, so our work is complete. With the points given, graphing this function would be very difficult without graphing technology. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.